Hello, this is the chapter 4.4, and we will talk about coordinate systems. So we talk about vector spaces and subspaces and the bases, and you're probably wondering, why do we need this basis in the spaces and subspaces? The main idea behind the bases are to introduce a system of coordinate. Basically, we're trying to make our vector space act more like Rn. So we want to step around, we want to find every single vector by stepping along predefined axis, which defined by bases. And even if we are dealing with Rn itself, it's still nice to have an alternative view of our vector spaces, which defined by the bases. So how we can do it? By introducing what's something else, coordinates, which is very simple way to say that this is just the weights in our linear combinations of given bases. So basically, if we are given bases from B1 to Bn in the vector space V, then we can express our vector x in coordinates of the basis B, or we call it B coordinates, which is just our vector will be equal the linear combinations of our basis vectors from B1 to Bn and some weights C1 and Cn. And we organize these weights from C1 to Cn as a vector, and we will call it a B coordinate vector. Okay, another way to introduce coordinate is actually using a transformation. We can say that we're going from the vector x to vector x and b coordinate by the coordinate mapping, or the mapping determined by the vectors b. Let's see how that works, because it's probably slightly mysterious. Let's just go through example and hopefully it will clear it a little bit. Let's consider a very simple two-dimensional vector space with a basis B1 and B2. And our B1 is vector 1, 0, and our vector B2 is vector 1, 2. Pretty straightforward example. So now we have a B coordinate vectors in this space, which has coordinate -2, 3. Let's just find this vector in, normal coordinate systems. And this is where it's very important to remember that our B coordinates is just weights, C1 and C2, which is basically, in our definition, C1 is the first coordinate component of vector B, and C2 is the second component of our vector B. So we can write it down explicitly. So our first weight -2 times vector B1 plus our second weight 3 times vector B2. And we write out explicitly our vector B1 and B2. And we can just add our two vectors and which give us the vector x is 1, 6. So in our normal standard R2 coordinate system. So, okay, let's just go ahead and now, just to practice, we will write our vector x, 1, 6 in the standard basis, which is in two-dimensional system, consists of the two vectors E1 and E2. Okay, so, and again, we are kind of break it down into the two parts. The first one will be vector 1, 0, so the component 1 should work, and the second weight will be 6, and it's multiplied by the second coordinate vector E2. And again, we can write it down as a linear combination. So basically what we get here is our vector x in normal standard basis will be just one step on the right toward the vector E1 and 6 steps up along the coordinates E2, and we can define our vector x. But now if we move to this our basis B1, B2, we basically introduce some kind of like good coordinate system. So we are using vector b1 and b2 as our basis. And because we have our vector x expressed in b coordinates, we can find it using our b coordinates. So basically, our b coordinate -2 means that we need to go in the we make 2 steps in the direction opposite to b1, get over there. So also our second coordinate equal 3 means that we need to make 3 steps in the direction of vector b2 over there. And again, we define our vector x. And it doesn't matter how we define vector x, it still be the same. It's just expressed in the different coordinates. And in some kind of applications, it's very convenient to use this kind of like shifted coordinate systems. And we will see it later in the next class when we'll start looking at the applications in Markov chains and dynamical systems. Okay, now this is the time to practice to translate from one coordinate system to another.